So in 12.1, we talked about discrete random variables, and we looked at an example of, looking at the grades on an exam, and that's very discrete because those are specific points of data that I can look at, and I can run an experiment from those. So the idea in this section is that we have a continuous random variable. So they give the example of, the age of a cell population. That really is continuous because at any moment in time, we can have a cell that's really any age. I mean, if we could be able to, if we had some sort of equipment sophisticated enough to determine the age of these cells, that is really continuous. I could have a cell that is 1 day old. I could have a cell that is 1.8 days old. I could have a cell that's 2.8759 days old. So the idea then with a continuous random variable is that instead of just having specific, maybe specific points that I actually have a function. So I'm not going to go over that example in the book. I'll let you read that. But if I have some function f of x, this basically is what we call our probability density function. So what I want to do is I want to give you some definitions to kind of put things together a little bit better, I think, than your book does. And then I'm just going to do some examples for you. So again, it should be a pretty easy kind of lecture today. That shouldn't take us too long. I know I say that often, but I really think so this time. So let's consider the function f of x, not dx, just f of x, okay? So then f of x is what we call a probability density function if a couple things are true, okay? So if the following are satisfied. Following are true, I think following are satisfied sounds fancier. All right, so probability density function is what I'm defining here. And what I want for the probability density function is I want to show a couple of things. First, I need to show that f of x is greater than or equal to 0 over some interval. So what I want to look at is I want to look at some interval over which this probability density function basically is, it's going to be a very simplified version of it. It's basically giving us the probability of something happening. And then 2, if I integrate this guy over that whole interval where this can possibly happen, then I should get 1. Okay, and so you read about that in the book. But the important part of that is to think about this probability, right? If I think about the probability of x occurring over the entire interval over which x is possible, it's 100% that that's going to be true. I mean, now I know exam grades aren't continuous, right? I can't have any possible exam grade. I can't have like an 80.753215. We don't grade that precisely. But if I could, then what is the interval I would integrate over if this function gave me the probability of, picking one of those scores? This function I would integrate from 0 to 100. So basically what that's asking is, what's the probability if I pick an exam score that one of them will lie between 0 and 100, where 0 is A and 100 is B? Well, that's 100% because those are the possible scores for the exam, okay? So that's kind of what we're talking about here. And then why does this need to be greater than 0? Because it's a probability density function. So I need my probabilities to be greater than 0. That's pretty much it. Okay, so like I told you, we're just going to do some examples. Okay, so the first example that I'd like to do is to verify that f of x equals 12x squared minus 12x cubed is a probability density function. I'm lazy, so I'm going to put PDF. I know that's not what that means in like society today, but I'm going to do that because I'm lazy. It's probability density function over the interval or for x. Ooh, I don't want -1. I made this mistake in my face-to-face class and it didn't work. So you guys are lucky I teach this in my face-to-face class first and I figure out all the mistakes. Usually 9.5 maybe was an example of when I didn't, but All right, so let's verify that this is a probability density function between 0 and 1. So the first thing is I need to show f of x is greater than or equal to 0 on my interval 0 to 1. So I am fine. If you want to just sketch a quick graph of this, you could graph this in your calculator. If you have questions on how to do that, let me know. I can algebraically showing it's greater than or it's positive over this interval. What we do is we look at the zeros of the function. So if I take a 12x out, 12x squared out, I get 1 minus x. So where do my zeros occur? My zeros occur at 0 and 1. And I really only care about this area right here. So if I pick a point in here, like maybe 1/2, well, 12 times 1/2 squared, that's positive. And then 1 minus 1/2 is positive. So sure enough, this function is positive between 0 and 1. That's one way you can show algebraically that it's positive as well. So again, for that first one to show me that it's positive, you could graph it if you wanted to using your calculator and then show me a quick graph of it. It doesn't have to be perfect. Or you can, what was I going to say? You can do this little trick where you do a little bit of algebra and then you find its zeros and then you test the function, kind of like when you do the first derivative test, but you're just using the function instead of the derivative. Okay, and so the next thing I need to do is I need to show that the integral from 0 to 1 of my function is 1. If I can show that, then it is a probability density function. So let's do that. So 0 to 1, 12x squared minus 12x cubed dx. And at this point in your career, I don't really need to do this for you, but we get 4x cubed minus 3x to the 4th, I believe, from 0 to 1. If I plug in 1, I get 4 minus 3. If I plug in 0, I get 0, and I get 1. So sure enough, we have a PDF, probability density function. It's something different than what it's determined to be now. Okay? All right, so let's do another example here that actually is finding probabilities, because that's kind of what we want to talk about. Okay, so here's my example. The shelf life of a certain drug has a probability density function. Okay, I'm going to be lazy. PDF. I'll just give this to you. It's f of x equals 50 over the x plus 50 quantity squared. Okay, and I got to give you some sort of interval, x greater than or equal to 0. Okay, so this has a probability density function of this for x greater than 0. So find the probability that a drug selected at random and again, this is a continuous random variable because really these shelf lives, if I just select a drug at random, it could really have any shelf life, right? Greater than 0. I mean, there's going to be some probability there, like, I mean, what's the probability of finding a drug that has a shelf life of 1,000,000 years? I don't know, but maybe there's some probability out there for that. Anyway, so it can be any number. It could have a shelf life of 2.753 years. So that's what we mean by continuous. So find the probability that a drug selected at random has a shelf life of okay, so let's do a couple of these. Let's say between 10 and 20 months. So, and I should have told you that. Sorry about that. X is in months. That's pretty important to know our units there. I don't always care about units because I'm what we call a pure mathematician. So I don't always care about units, and my physicist colleague hates that. But that's probably important. Okay, so here's going to be my notation, and I probably should have put this in our definition back there. But so this is kind of a new definition. If you want, you could go and add that back to your in your definition on that first page that we did. This right here, this notation says, what is the probability that if I select X at random, it will lie between A and B? Okay, and the way that we calculate that is we just take the integral of my probability density function from A to B. So what I'm asking here is, what is the probability that if I select a drug at random, that's my continuous random variable, we'll call it X, and I believe these are capital X's. Sorry about that. What is the probability that if I select a drug at random, its shelf life will lie between 10 and, lie between? I don't care. I'm not an English teacher. Lay between 10 and 20. Okay. So that's what this is asking. So I'm going to integrate my function between 10 and 20. So remember, this gives me the probability of that occurring. And what do I want? I basically want to add up. Basically, think about what an integral does. An integral basically, this is a very generic way to say this, but an integral basically allows us to add up an infinite number of things. So what this is doing then is this is adding up basically all of the probabilities between 10 and 20. That's kind of the idea here. Not that I can actually find a probability at a certain number, because I can't, find between 10 and 10. But that's kind of the idea here, is that we're looking at all the possibilities, the probability of getting 10, of getting 10.5, of getting 10.11, of getting 15, and adding all those probabilities together. And by integrating it, that's what it does for us. I'm going to rewrite this a little bit. Again, I don't know why I have a negative, because I was thinking about bringing that up. I don't think you need help integrating these. If you do need help integrating these, then you need to be spending some more time on this stuff, or you should be emailing me and asking me questions. So if I add 1 to this, I get -1, right? If I divide, and then I'm going to divide by -1. So I'm going to do a little side work up here. And then remember, I have to divide by the derivative of the inside, but the derivative of the inside is just 1. So it looks like I get a -50 over x plus 50 evaluated from 10 to 20. Okay, so if I plug that in, I get a -50 over 70 minus a -50 over 60. And so I believe, let me grab my calculator. It was in my bag. That's basically a -5/7 plus 5/6. And that's 540 seconds. But I don't know about you, but that doesn't really mean much to me. What is my probability? I'm running out of room. My probability is 0.119. So if I take a drug if I just take a random drug at random, what is the probability that its shelf life will be between 10 and 20 months? It's 11.9%. Okay. All right, let's look at another part of this. Let me just clear this out. Maybe. There we go. So part B of the same problem. What is the probability that if I take if I grab a drug from random, or at random, that its shelf life is at most 25 months. So what do I want to find the probability of? Well, at most 25 months, that means it can be between 0, again, this is a capital X, and 25, right? But not more than 25. So again, we get this situation where I'm integrating the same function. Okay, I know what the antiderivative is, and I'm going to tell you right now, because I'm not really going to go over this, I don't think. You can look at this in your book. This is the cumulative density function, the antiderivative, and they talk a bit about why that's important. So whenever they ask you about the cumulative density function, it's just the antiderivative of the probability density function. So don't let that confuse you too much. It's just an easy way basically to find probabilities, because every time I want to find a probability, right, or a range here, every time I want to find that probability of x lying in a range, I need the antiderivative to evaluate the integral. So when they talk in your book about the cumulative density function, all they're asking you to find is the antiderivative, and then plug the numbers into the antiderivative. So they're basically taking 2 steps. They're asking you to find the cumulative density function and then plug in the bounds. So I hope that kind of makes sense. So if I put in 25, I get a negative 50 over 75. If I plug in 0, I have a negative 50 over 50. Okay, so I basically get negative 5/7 plus 1. And so that, oh, I didn't need, why did I need my calculator to do that? Oh, Sarah, how embarrassing. All right, so this is 0.28, I'm just gonna round 6. So we get about 28.6%. So if I grab again, and again, you gotta remember with probabilities and experiments that we need to understand that if we did this experiment over and over and over, right? And then we recorded the shelf lives, that 28.6% of the time, the shelf life of my drug would be at most 25 months. So understand that too. Experiments are things that run over and over again. If I continually do this, then my rates will tend toward 28.6. You might not get 28.6 the first time. You know, we get closer and closer to it. All right, and the last one I want to do is what if we, what is the probability that I grab a drug at random and its shelf life is at least 25 months? So I like this one because it's super interesting. I know my idea of interesting and your idea of interesting are different, but that's okay. So what do I want X to be? I want it to be at least 25. So I want it to be greater than or equal to 25. So what does that mean? That means it can be 25 or bigger. So I'm going to go up to infinity. So I know I'm excited. I know you are too. We're getting improper here with our improper integrals. So remember, we need to replace that infinity with a b. Well, let me do it here first. Okay, because remember my fundamental theorem has no idea what to do with infinity. Infinity is not a number. It only knows it's an idea, it's a concept, right? So now again, I know the antiderivative, and again, that's your cumulative density function if they ask you for that. And now I'm going to evaluate this from 25 to b. Okay, so if I plug this in, I'm still going to notice how I carry my limit signs through. Limit as b goes to infinity, I get a negative 50 over b plus 25. And then if I put in the 25, this actually becomes plus 5/7 if I simplify a little bit. And then what happens is this guy goes to 0. Remember, if the denominator is getting really, really big, the numerator is staying constant, that guy's going to 0. So I get 5/7. And if I divide 5/7, I get about 71.4. Now, people, this should be making sense to you. Well, it's easy to say that. It should be making sense to you. But look at this. Look at what I found in B. In B, I wanted to know what's the probability that the shelf life is at most 25 months. That's 2/7. And then I found the probability that it's at least 25 months. That's 5/7. So that makes sense, right? Because if I think about it, this guy basically looked at what's the probability I get a shelf life up to 25. Then this guy looked at what is the probability I get more than 25. Those two things should equal 1, right? Those probabilities. If I had asked, what's the probability that it's either at most 25 or at least 25, well, that would be 1 because that would cover the whole thing. So I hope that makes sense. I'm sorry, I'm about to sneeze. Oh, okay. All right. So let's look at, I want to just say a couple things about the cumulative density function, and I'm going to let you read at kind of the last half of page 561. They kind of describe the cumulative density function, which isn't, you know, it's fine. It's fine. It's an interesting function, but if we let f of x be our probability density function, density function, then the cumulative and you saw this in the book, but the cumulative density function, I said this was going to be a short lecture. Darn it, Sarah. I really wasn't going to define all this, but I think I probably should. Then what are we defining here? The cumulative density function, okay, is a function. We're going to call it capital F of x, such that, couple things here, okay? I want to define a couple things. First of all, big F primed of x equals little f of x. So this is what I was talking about when we look at the cumulative density function. It is just going to be the antiderivative. Well, not just, but it's going to be the antiderivative. Well, yeah, it is. It's going to be the antiderivative because I'm going to find that c, but it's going to be the antiderivative of our probability density function, okay? So that's important. Another thing that is important here is that f of x, okay, is just going to be the probability, and if this was a little x, this would be just the probability that x is between, capital X, is between a and little x. Another thing I want to add to that is that if I take f of big A, that must equal 0, and f of big B must equal 1, okay? What this is basically saying is if I'm taking that cumulative density function, if I look at the probability that I lie between A and A, well, that's 0, right? I can't lie between those two numbers. And then if I look at the probability that I lie between A and B, right? So look at what I've done here. I've just replaced that little x with B. That must be 1 because little f is a probability density function. Oh, whoa, look at what I did there. I don't want to do that. All right, and then 3, the other thing that's interesting about the cumulative density function, and this we already know, but how is it related to the probability, finding probabilities? Well, that's a capital X, I keep doing that. Because we know that the probability is just A to B of my probability density function, I know that I just take big F of B minus big F of A. So those are the important things, and I wish your book would like put those together a little bit better. Those are the important things about the cumulative density function. Okay, so the thing I kind of wanted to show you that's important about this is, let's do another example. And one example, and then I promise we'll be done. If you haven't already left, and if you've already left, you don't hear me saying this anyway. Okay, so find the cumulative density function, I'm gonna call that CDF, for the probability density function, little f of x equals 12x squared minus 12x cubed. We know it's a probability density function because we proved that for x is between 0 and 1. Then use it to compute the probability that my random variable is less than or is between 0.1 and 0.9. Sorry about that. Okay, so I know that big F is just the antiderivative of 12x squared minus 12x cubed dx, which we saw before, right, was 4x cubed minus 3x to the 4th, I believe. But now I have this plus c. So how do I find the c? Well, I know, remember, that f of a must equal 0. So as long as I have a condition that I know then that f of 0 must equal 0. So that would be 4 times 0 cubed. This does not always equal 0, so make sure you check that. Plus c must equal 0. So in this case it does, right? But it doesn't always mean that. Okay, so my cumulative density function then, so what do I get for this? And these are little x's. F of x here, big F, is 4x cubed minus 3x to the 4th. And then how do I find this probability that my random variable, my continuous random variable, that's capital X, and sometimes we'll put lines on it so you know it's capital, is between 0.1 and 0.9. Well, the nice thing about finding the cumulative density function, because we know it's the antiderivative, you just take f of 0.9, capital F, minus capital F of 0.1. Okay, so I'm going to plug in 0.9 cubed minus, not times, minus 3 times 0.9 to the fourth, and then minus, parentheses, 4 times 0.1 cubed minus 3 times 0.1 to the fourth. I don't really trust myself that I'm doing this, but 0.944. I actually feel pretty good about that. Why do I feel pretty good about that? Because I know that the probability of going over the entire interval from 0 to 1 is 1, or 100%, right? But I'm looking between what, 0.1 and 0.9. So, you know, if this is my interval 0 to 1, what I'm looking at here is 0.1 to 0.9. I've almost grabbed that entire interval. So I would expect to be pretty close to 100%. All right, people, that was not a short lecture. I continually lie to you about this. As always, let me know if you have any questions. Have fun.